Hi, my name is Nathan, and this is the final presentation for my project, HandMap. To start with, I'll quickly go over what we did last time. We looked at the dlib classification and detection method, and also real-time distance mapping. We got it working, but it wasn't overly optimal, and we found that there was a limitation in which that the reference object needed to be the leftmost object in a given scene. In this video, I look at one of the existing solutions to the problem in the market and see how it compares to mine. I also take one of the methods they use and implement it myself to see if its viability. Then after that, I begin to resolve the problems with merging my distance and angle mapping techniques into one finished solution. And then finally, I outline where my project's up to and what needs to be done next. I stumbled across a project called Curatio, which is starting to appear more and more in the professional medical space. It uses 32 Raspberry Pi cameras and laser pointers to create a 3D point cloud of an object in the center. It is more targeted towards the professional medical space because of the excess hardware required to set it up. It's not really suitable for the individual consumer. I did off-the-cuff estimate of how much all the equipment would cost, and I came to roughly 14,500 Australian dollars, which is definitely not really viable for individual use cases. Although the core concept of Curatio doesn't really fit my needs, I did want to look into what kind of technology they used in order to capture, map, and create a mesh of an object. I did a little bit of research and found that the most likely case would be that they were using scale invariant feature transform, which is SIFT for short. And basically, this method looks at shared features of a similar object from different angles. And it can use those shared features to compute scale and build a point cloud based on those scale measurements. Another thing worth noting is that Curatio offloads this very computationally intensive task to the 32 Raspberry Pi cores. Although I was starting to have my doubts about whether or not this would work for mobile, I did want to run the test myself, so I captured 884 individual photos of my hand next to the blue cube as my sample image set. I should note that I didn't actually take 884 pictures. I just took a video file of me surrounding my hand and then extracted each individual frame. Details of the technical process I followed to do the following experiment is outlined on my project blog, but basically after the initial map, which took 20 minutes, I came to this image, which, as you can see, contains all these little colored pyramids. They represent camera angles or positions where the algorithm has computed where the location of the camera was when the image was taken. And believe it or not, the map we just generated was just the sparse one. I then generated the dense map, which was 79 minutes worth of computation. I should note that the number of images that I input was far too big. Typically you would use maybe from 30 to 50 images of a higher quality. That way you get the detail without needing to run so many iterations over the same images. Finally, I simply opened the output files in MeshLab and I had my 3D model of the hand and brick. So what did I kind of learn from this? Well, I learned that my output was significantly worse than the output from Curatio. And I also learned that SIFT is probably too computationally intense for running on mobile. It works for Curatio very well because of the fixed camera positions that the Raspberry Pis are in when they take the image. This level of detail is just not going to be possible for me at this stage, but later on down the track I would like to look into using SIFT as a supporting method for my angle and distance measuring. At this point, I went back and had a look at my code that mapped angles from a reference object. The reference object in an image was the leftmost largest contour, which wasn't very modular, so I came up with a new solution. I used RGB detection to find an object within two given RGB ranges. The object that had the largest contour within these two ranges was declared my source and or target image. And you can see the code on the right kind of outlines how I did this. It is very similar to how I did color detection in the past. The final task I had to overcome was how do I bring this all together? So I had a look at my existing angle mapping code, and I noticed that really there was just one single line that did all the work because I'd already calculated the center of various objects in the distance and measurement tracking. So I simply imported this single line into that code and I basically had a working solution. It kind of was quite simple, which was very surprising. So there's an example on the right hand side of me mapping the angles and the distances to little red dots on the ends of my fingers from the blue reference object at the bottom of the screen. So now I'll just quickly go over some of the current issues that I'm having in case somebody wanted to jump on board and take this project on. Depth of field is the biggest issue. Right now, if you have a look at the image on the right hand side with the lady's hand, you can see that although these 2 points look like they're quite far away from each other from that perspective, they are actually pretty much next to each other in terms of length when the finger's not bent. So we need to come up with a way to handle perspective practically. Currently there is no real way of doing that with my solution unless you're taking the photo from either right above or on the side. I'd like to use some of the gravitational and orientation data from Wei Yang's sensor and the mobile phone's sensors while taking the photo, because this would potentially allow me to calculate the offset that the camera is angled to when looking down on the hand. Again, a little bit more research would need to be put into this before I could say for sure whether or not it would work. Future plans for this project include generating a mesh using captured data points, which we could turn into a point cloud, and then see if we could use the SIFT methods discussed before after the fact to see if we can improve the quality of the output. Again, a little bit more work would need to be put into seeing if we could use 3 or 4 photos to fill in the gaps effectively. Then we could compare this mesh with the actual measurements of the hand to see just how viable the solution really is. And the final plan would be to get it all running on a mobile phone. Finally, it would be really good to look into the potential of 3D printing the splints after the mesh has been generated. I'd need to look into partnering with some local medical centres or PMH to see if we could trial the solution on some of their existing patients. I'd also like to look into contacting healthprint.io and consult with them on whether or not they do 3D manufacturing, and if they do, to see if they've got a supply chain or a distribution chain that we could use to distribute the splints to patients worldwide. Now, this slide sort of marks the end of the project for me for the semester. I'd just like to say thank you to everybody who sort of gave me ideas and supported me over the past 8 to 12 months as I've kind of been learning and investigating and coming up with what I think is a fairly viable solution. As always, all information regarding my project and the code base for the solutions that you've seen outlined in this video are available on handmap.github.io, or you can flick me an email at nathan@glovers.id.au if you have any questions. Thanks very much.